All right, so are we good to get going, Jason?
Yep, should be good. I'm ready when you guys are.
All right, Gina, if you want to start sharing screen and I can do your introduction today.
Okay, great. All right, you should be able to see my screen and now it's in presentation mode.
All right, perfect. Welcome everyone. Today we have Dr. Gina DiBraccio, who is the Associate Chief of the Planetary Magnetospheres Lab at NASA Goddard Space Flight Center. Gina joined the Goddard Magnetometry Group in 2014, where she began working on the MAVEN mission to Mars. Her research focuses on solar wind planetary interactions through magnetic fields and the analysis of data from magnetometers. Gina has explored the magnetospheres of Mercury, Mars, Jupiter, Saturn, and even of the ice giants. Currently, she is the project scientist and on the MAVEN magnetometer instrument and is the deputy lead on the magnetometer instrument, a part of the STORM Phase A mission concept study. So I'm Gina, who's going to be talking about Fluxgate magnetometers for space exploration. We'll also be answering questions at the end of the seminar. So if you would like to, if you have any questions, please put them into the chat box and we will have a nice discussion at the end. So Gina, when you're ready.
Okay, thanks so much. So as I said, I'll be talking about Fluxgate magnetometers for space exploration. And I am part of one of the magnetometer groups at NASA Goddard in the Planetary Magnetospheres Lab. As I mentioned, I'm also the project scientist of NASA's MAVEN mission. And for that reason, as I go through this talk, you'll see some of the examples from MAVEN's magnetometer directly. All right. Let's see. So here's a quick outline of the talk, just so you understand the flow of where we'll go for the next hour or so. I'll start by giving you an overview of Fluxgate magnetometers, and then I'll give you a spotlight on ring core Fluxgates specifically that we'll be focusing on. I'll talk to you about how the ring core Fluxgate magnetometers work, and then I'll get into spacecraft magnetic control plans, which aren't specific to ring core Fluxgates, but magnetometers in general. I'll talk to you about pre and in-flight calibration, and then we'll get into exploring magnetospheres with Fluxgates. Considering this is a magnetosphere seminar, I figured that the audience would be interested in hearing about some of the science that we can do with our instruments. If you look over at the right, this figure that I have showing you here, these are the fully assembled magnetometers on board MAVEN. So we have two magnetometers and the electronics boards to go along with it. I'll talk to you about that in more detail as well. Sorry, having a little trouble advancing the slides here. There we go. Okay, so I want to start out by just saying thanks to my team at Goddard. As I'm here giving you the talk, I am not the single expert on absolutely everything to do with these Fluxgate magnetometers. We have this entire team filled with technicians and engineers, scientists, postdocs, students, and that is what makes our the magnetometers from our group at Goddard a success, at least, because we have all of these experts on the different factors here. So our group is able to actually come up with the scientific concept of what it is that we'd like to study. We have our engineers and our technicians in the lab who actually create the hardware and bring that idea to life. We fly our instruments to various planets throughout the solar system, and we have scientists such as myself that are able to help calibrate and process the data, but also analyze it scientifically. And so these are just the faces of my team that make all of this possible from the Goddard magnetometry standpoint. Let's see, my slides do not want to advance. There we go. Okay, let's start with the motivation of why should we measure magnetic fields in space? Well, magnetic fields are omnipresent. They're everywhere throughout the universe. As many of you know on this call, planetary magnetospheres are filled with magnetic fields. The magnetic fields of the sun emanate throughout interplanetary space. We also have magnetic fields that are out of our heliosphere in interstellar space. And so when we measure magnetic fields, we gain knowledge about the fundamental characteristics of the environments both within and around objects in our solar system, and beyond as well, as I'll be showing you some Voyager measurements at the end of this talk. But magnetic field measurements are crucial to help us understand a variety of things, including charged particle motion through space as charged particles and magnetic fields are coupled together. It allows us to probe the deep interior of planetary bodies, not just to understand the magnetic dynamo and how those are formed, but also the internal structure of planets and different bodies. And we can also probe to determine whether a subsurface ocean is present or not. We can monitor the sun's magnetic field and its influence throughout the heliosphere. And what this means is not just for typical solar wind and IMF conditions, but also for space weather events. And then finally, we can characterize the planetary magnetic environment at different bodies throughout the solar system and really understand what planetary magnetospheres are doing as far as their magnetic characteristics are concerned. So what is a magnetometer? Now, I'm going to use this definition that was quoted by Mario Acuna himself. Many of you are at least familiar with the name, as he was one of the leaders in space-based magnetometers. And in fact, I'm showing you at the bottom here just a clip of a paper that I highly recommend you read if you want to learn more about space magnetometry, and you can see the DOI here. But really, I couldn't have said it better than Mario himself, so I will read his quote directly, which is, "Magnetometry is the science of accurate measurements of the strength and direction of magnetic fields, and space magnetometry represents the specialized science of making magnetic field measurements in space aboard vehicles such as rockets, balloons, and spacecraft." So magnetometers are used to measure the strength and the direction of magnetic fields. There are two different classes of magnetometers. There are scalar magnetometers, which only measure the magnitude of the ambient field. And then there are vector magnetometers. And vector magnetometers can measure the strength and the direction of the magnetic field. So there are various types of magnetometers, but as the title of this talk said, I'll be focusing on Fluxgate magnetometers. The history of Fluxgate magnetometers, let's get into that a little bit. So the first patent was applied for in 1931, and the first sensor was developed to measure weak magnetic fields in 1936. So Fluxgates were actually used during World War II as a submarine detector. And those are the figures and the images that I'm showing you at the bottom of the page here. This is actually a fully assembled magnetometer from World War II era used to detect these submarines. So they were part of naval warfare here. On the right, you can see in this cartoon, the aircraft actually flies with the magnetometer out the back, and it's able to be oriented in order to detect these different magnetic fields that were being given off by the submarines. But after World War II and even during, the Fluxgates were used for other purposes, as such as geophysical prospecting, airborne field mapping, and later they actually became the most common type of instrument used in space platforms. So space magnetometry itself began by exploring the Earth's magnetic field in the 1950s. So let's get into the details of a Fluxgate magnetometer a little bit more here, starting with the components. The basic components of a space-based Fluxgate magnetometer includes three different parts, if we want to break it down very simply. We have the Fluxgate sensor, and there are various geometries to the Fluxgate sensor, and I'll show you a couple examples of that. We have the Fluxgate electronics, and then we have the wiring harness, which connects the sensor and the electronics together. So over on the left, this is the MAVEN mag sensor, one of our two magnetometers that are flying on MAVEN as we speak. And so you can see kind of the geometry of the sensor that we have here. On the bottom right, these are the MAVEN electronics that go along with the sensor here. Now, if you look at the left, these are the fully assembled MAVEN mags, and you'll notice these kind of ropes that are coming out from the sensors. These are the wiring harnesses, and they're very important because often the electronics of the magnetometers are housed within the spacecraft body itself, but the sensor is far away from the spacecraft. We try to get that far away to mitigate for fields that are coming off the spacecraft. And so for that reason, we need this wiring harness that varies in length to connect the sensor and the electronics based on how far the sensor actually is away from the spacecraft itself. So for the purpose of this talk, I'll be talking about ring core Fluxgate magnetometers because there are a variety of different type of Fluxgates themselves, depending on what the heart of the sensor actually is. But for the type of geometry that's utilized in my group, and actually the type that's most common for space exploration, are these ring cores. So those are the details that I'll be getting into here. So the ring core components consist of a permalloy ring core, which you can see in the center here. We have a picture of one of our ring cores that we use. We have sense units that are over here on the right. You can see it essentially looks like a solenoid. And then the other components include a small circuit board that are used for wire transitions, tuning capacitors, temperature sensors. We have non-magnetic resistive heater tape, and then other components to assemble the entire structure, such as the sensor body, the cover, the attachment points. But one thing that I do want to point out is we need our parts to be non-magnetic because we are trying to measure magnetic fields. And so, of course, we don't want our own instrument to interfere with the measurements that we're trying to make itself. So getting into the detail a little bit more about the ring core components that break it down, essentially, there's a bobbin that we start with for the ring core. Then we have permalloy material that's wrapped around the bobbin. We have capped on tape that then goes around that. And then the ring core is finished off with a drive winding, a magnetic wire that's wrapped around everything there. Now, the properties of the ring core are crucial to the instrument's sensitivity. And this permalloy material is special to the ring core because it has very unique characteristics that enable us to make these measurements. So it has a high magnetic permeability, but it also easily changes magnetization. If you look at the images on the left, this is from the recent publication by Miles et al., showing you kind of the different points in constructing the ring core. We start out with that bobbin, and then the permalloy material is wrapped around the bobbin. Panel C is the same, except now it's been heat treated. Then there's that layer of capped on tape, and then a drive winding that's wrapped around. The sense unit, as I mentioned, is essentially a solenoid, and this solenoid is created by wrapping a sense winding around a bobbin. So you'll see I have a cartoon of a bobbin right here, and we take a magnetic wire similar to that drive wire that you saw for the ring core, wrap it around for the sense winding, and we create this solenoid. Now, the sense unit is used to determine a single axis when we're measuring magnetic fields. However, we can couple two sense units in order to measure two different axes. So if you look at the picture that I'm showing you from our lab on the right, this is actually showing you how two different sense units are combined orthogonally to each other to measure two different components of the magnetic field. And I'll get into this in more detail as well. So here's how the ring core is actually assembled here, the sensor itself. We have the ring core, then we have those two sense units. We have an inner sense unit and an outer sense unit. And so as I click here, you'll see a video of how they're constructed. The ring core goes right into that inner sense unit, which then slides into the outer sense unit. Again, those sense units are orthogonal to each other, which is crucial to be able to measure two orthogonal components of the magnetic field. So now let's talk about how the ring core fluxgate actually works. So the drive winding that's going around the ring core is being used to drive the permalloy core material into and out of saturation. And we do this by applying an alternating current. So the permeability of that core material is going to change when it's saturated and when it's unsaturated. And this actually affects its response to the background field. So while the core is driven into and out of saturation, that sense unit that's around the ring core is going to gate the flux by measuring a voltage that's produced when the flux is going in and out of the drive winding. So if you look at this figure that I have on the right, we can talk it through in a little more detail here. Two different scenarios when that permalloy material is unsaturated at the top and saturated at the bottom here. We have these hysteresis curves that essentially show where the current is that's being applied. So as I said, we're applying an alternating current to that drive winding. So it's going in one direction, in the positive direction, then it comes down to the negative direction. So for the top scenario that you see, the shaded region is when there's very little current or close to zero current being applied. And so when it's out of saturation, you're getting a scenario that the permeability is high in that permalloy material, and therefore the sense winding is able to sense that background field because there's room within that material for the background field to be measured within the structure here. Now, if we go down to the saturated scenario, when we look at the hysteresis curve, that means we're either near that positive current or the negative current, but essentially we've driven that permalloy material to saturation So now its permeability is low and it can't actually measure that background field. It's essentially full when it's saturated. And so it's pushing out that background material, in which case you can see the way it's drawn, the background magnetic field is not being sensed by that sense coil. And so as we go into and out of saturation by alternating this current, you get this scenario where that background flux, if the magnetic field in the background is present, is going in and out of that ring core. And so that's going to drive the voltage that the sense unit is able to measure. So talking about it a little bit more, the geometry of the Fluxgate core and the drive windings matter. So in that simple scenario that I showed you on the last slide, we were essentially looking at what appeared to be a single solenoid for that sense unit. But now we're going to take it one step further to talk about the geometry when I introduced to you here, this square bobbin. So in this square bobbin, what we've done is we've created a split in the drive winding. So this yellow wraps around a single drive winding that's the same that was applied to the ring core, although now we've oriented it such that when that current is applied in either direction, it's going to generate magnetic fields that are anti-parallel to each other. So I'm showing you a scenario of driving a current in a certain direction where on the right side, it's going to produce a field going up where you see this red arrow, and then on the left side, it would produce a field that's going down with this green arrow. Now, the drive waveform without a background field would look like something that I'm circling right here at the top, where you see that the fields are equal in amplitude, but opposite in direction. So they'll cancel each other out here. And so what that means is that the sense winding is not going to be sensitive to what's going on here because these fields are canceling each other out. However, if we're in the presence of a background field, what you're seeing in the scenario at the bottom here, now we're able to measure the background field with that sense unit because those fields, the red and the green fields, are still canceling each other out, but there's a general shift upward with that increase in magnitude since the background field's present. And you'll see that by the dashed lines here. And so that just goes to show that we can utilize a different geometry in the core of the Fluxgate in order to measure these background fields that we're looking for. So if we want to take it one step further, and you can assume now instead of splitting the drive winding just on two sides of the square, let's split the drive winding around all four sides of the square. And now you're going to take your square and push in the corners so that you create a circle, and then you have the geometry of a ring core. Okay, and so going with that same train of thought, if you think of the ring core as kind of being cut in half with a field generated on either side with that similar geometry, we still have those red fields and green fields that will cancel each other out. And now this is simplified, of course, but it's giving you the idea of how the Fluxgate, the ring core geometry, is going to work here to sense those background fields. So we have these, we're driving the current in, and it's generating the magnetic fields that the sense unit is going to measure. So what we do is we have that sense unit that's over top of the ring core, and it's going to sense a magnetic field in a direction depending on how you orient the sense unit because it's a solenoid. And so we can get one component, of the magnetic field. And then as I showed you earlier, we'll put an orthogonal sense unit on top of that in order to get a second component of the magnetic field. And so it's this ring core sense unit combination that makes up the sensor. However, what I'm showing you here is just measuring two of the components of the magnetic field. And of course, we want 3 axes, right? So we'll use 2 of these combinations in order to get that third axis. And what that means is that we're technically measuring 4 axes of the magnetic field, but 1 will be redundant. So we have 3 axes that we're measuring with the Fluxgate magnetometer to get that vector magnetic field, but 1 of the axes is typically redundant there. So as I said, for our fully assembled Fluxgates, we have that 1 ring core and the 2 sense units to measure 2 axes. The sensor consists of 2 of those sets. And one thing that I mentioned as far as the sense unit is concerned is that those sense units have to be orthogonal to each other, and that's crucial for measuring the axes. But we actually, the way that we orient the units of the sense units and the ring cores together on the fluxgate themselves on the base, the orthogonality there is important too. And so I'm showing you the Juno magnetometer sensor as well that we developed in our lab at Goddard. And as you'll see, we have this sense unit that's horizontal here, and housed within it that you saw in the earlier videos, but you can't actually see in this picture, is another inner sense unit and a ring core. And so we have that here, but now we have the second set and it's vertical. So these are situated orthogonal to each other as well. And that's crucial for getting all three of the axes of the magnetic field. And so this orthogonality is something that's really important when we're building the hardware in the lab. And it's something that we calibrate and test for as well prior to flight. But one thing that I wanted to mention is that our instruments fluxgates in general are tailored for mission needs based on the measurement requirements and the environment requirements. So the materials that are used, or even how many wraps of the wire that are going around the sense units, varies based on the thermal constraints or the radiation of the environment, the measurements that we're looking to take. And so it's something that we can tailor based on mission needs. If you look at the right, this is a picture of one of our engineers, Jim, in the lab building, I think those are the MAVEN magnetometer sensors actually, so prior to launch. And so ring cores are also, they also come in miniature form, and these small mags are ideal for resource constrained missions, various small sat missions, and they require less resources without sacrificing the science. So the small ring core that's used in these small mags is 1/2 inch in diameter. And that's compared to the standard mags that have a ring core of 1 inch in diameter. So within my group at Goddard, the small mags that we offer are based on heritage from the POGS mission that has flown at Earth in the 1990s. So showing you just some of the pictures of the small mag components. Looking at the left, here is the small ring core, that 1/2 inch in diameter, along with the sense units to go with it compared to the size of the quarter. So you can see how tiny they really are. In the center, this is a picture of the POGS mag that, as I said, was flown at Earth. And then over on the right, here's a picture of me holding a small mag that will be flown on the GTOSat mission in the near future. On this board, the sensor itself is just at the top. You can see how small it actually is. And then this rope that you see along the length of the board is the harness that will connect that sensor to the electronics when it's assembled on the small sat. So here I am just showing you a table that compares the difference between the standard and the small size ring core fluxgates that have been developed in my group at NASA Goddard. There's also another group at Goddard developing small magnetometers as well, but they utilize a different fluxgate geometry rather than the ring core. So just for comparing apples to apples here, I'll keep the ring cores on the table. But essentially what you can see is that these are both low mass and low power, but they have a high heritage. And the measurement capability that they offer is reasonable for most science. And again, this depends on mission requirements. But for the standard size fluxgate, you can see the measurement capability is about 0.01 nanotesla. And then the small ring core offers 0.1 nanotesla. And so although it's an order of magnitude different, that's something that allows you to achieve most of the science that a lot of scientists are looking to do with the magnetometer measurements. The sensor mass for standard is about 400 grams with power of less than 1 watt. And then for the small ring core, the sensor mass itself is as low as 30 grams and then requires about less than 0.5 watts. In the picture that you see here, this is just a variety of the various missions developed in our lab, the magnetometers that are flying or will fly. And so we have developed and built the GOES magnetometers, and we're continuing to do so for future GOES missions. We have the MAVEN magnetometers as well, the Parker Solar Probe magnetometer. And as I mentioned, you saw on the last slide, the GTOSat small mag will be flying soon as well. You've also seen a picture of the Juno mag, which is flying at Jupiter currently. Okay, so once our fluxgate is fully assembled, now we have to think about applying a magnetic cleanliness plan in order to characterize magnetic sources that are coming from the spacecraft, but also to calibrate the instrument as well. So the magnetometer location on the spacecraft itself is going to play a crucial role as far as how much magnetic cleanliness needs to be mitigated, essentially. So a spacecraft magnetic control plan identifies fields that are generated by the spacecraft components, the subsystems, and the instruments. And the magnetometer calibration is performed both prior to flight and during flight. So we're going to calibrate the orthogonality and the scale factors and the offsets prior to flight. And then in flight, we are able to still calibrate the offsets as well. But you should know that the magnetic cleanliness requirements can be balanced with the use of a longer boom, depending on what the mission requirements are. And so it all depends, it all comes back to the requirements of the mission, what you need to do for magnetic cleanliness, how strict you need to be, or if something as just using a longer boom could mitigate for that. So as far as a spacecraft magnetic control plan is concerned, as I alluded in the last slide, spacecrafts generate both static and time-varying magnetic fields, and these can obviously interfere with measurements of the ambient magnetic field. Now, the spacecraft magnetic control plan can track the expected fields at the magnetometer location, and a variety of testing is implemented in order to both identify and reduce magnetic sources. And so here I'm listing just a couple examples of ways that testing and mitigation is implemented. And the first one that I'm talking about is the spacecraft swing test. So looking over at the right here, this is the magnetic swing test that was performed on the Parker Solar Probe spacecraft prior to launch. And if you have time, you can Google this later and actually watch the video of them hanging the spacecraft in the clean room and pulling it so that it can swing back and forth. And so this very expensive spacecraft is hung and swung back and forth in order to identify the magnetic sources that it gives off. And so this is done with other magnetometers around in order to understand what sources could be coming from the spacecraft and interfere with some of our measurements. And I will actually show you a few examples of spacecraft fields that we're able to measure in space. Magnetic compatibility tests are performed where different components of the spacecraft are energized so that we can see what magnetic signature they give off. And there are different magnetic tests of individual instruments and subsystems as well. Now, one thing, if the spacecraft has solar arrays, one technique that has been implemented is to actually backwire the solar array in order to compensate for the currents that are driven to power the solar arrays, because of course those currents will then create a field that we can measure. And so backwiring the solar arrays is one technique that has been successful for magnetic cleanliness. And then finally, it's possible to keep a spacecraft model, magnetic model, so that during the life of the mission, as different things are turned on and off on the spacecraft, we're able to see what the magnetic fields of the spacecraft are actually, what they look like. So magnetometer booms, magnetometers are often mounted, as I said earlier, we want to put them far away from the spacecraft to get away from any fields that the spacecraft is generating. And so we often use these deployable booms to extend the instrument away from these spacecraft fields. The boom length vary among missions. And so it's a question that we often get is how long of a boom do you want? And there are many trade-offs here, right? So there's trade-offs between what the length of the boom is versus the level of magnetic cleanliness that's required. How accurate do you need those measurements from the magnetometer to be? But the length of the boom is also going to be limited by the alignment requirements because we need to maintain that attitude determination for accurate measurements as well. So if you have an extremely long boom that isn't rigid, then the attitude determination might not be as accurate. And so we also have to consider spacecraft dynamics as well. Is it a spinning spacecraft? Is it a three-axis stabilized spacecraft? And of course, there are various boom styles, and this also depends on the mission needs, but the cost constraints too. You can have something as simple as a stick boom, or you can have something as sophisticated as an astromass boom, which you can see in these figures on the left here, these pictures of both the undeployed and the deployed astromass booms. So along with the booms, we can utilize the dual magnetometer method, which is a technique where two magnetometers are mounted on the same boom at different locations from the spacecraft. And this is actually based on observations that most spacecraft fields will start to decrease as a simple dipole when you get far enough from the spacecraft itself. And so it falls off as that 1/r cubed based on these observations. And so what we can do is we can utilize measurements from two magnetometers along the same boom at different lengths from the spacecraft in order to separate the spacecraft field from the ambient fields. And so this dual mag method actually enables the use of shorter booms while maintaining those high high accuracy measurements that we're looking for of the ambient magnetic field. And in this figure here, you can just kind of get a sense of the spacecraft at the center of the box here with a boom going out and having these magnetometers at various points, typically referred to as the inboard mag and the outboard mag, in order to mitigate from those spacecraft fields, remove those spacecraft fields, but be able to measure the ambient magnetic field with a higher level of accuracy. And so the Voyager mission actually utilized this dual magnetometer method. The Voyager 1 and 2 spacecraft actually both had these dual magnetometers on a single extended boom. And so Voyager utilized astromass booms that were 13 meters long. And you can see in this nice graphic on the left, there are 2 Fluxgate magnetometers on this astromass boom, one at the very end, 13 meters from the spacecraft, and then another one that was just over halfway down this boom. On the right, you can see in the lab prior to launch, this is one of the Voyager booms that were being deployed just to test it out here. And so the measurement requirements for Voyager were very high for such a great mission that was a once in a lifetime opportunity. Not only did they get a very long boom, but they were able to utilize this dual magnetometer method for that as well. But I also wanted to give you a sense of the different options and the different ways that MAG sensors are located on various spacecraft that are taking measurements as we speak today at various planets. So to start, I showed you a picture of the Juno MAG sensor. Now this is a picture of the Juno spacecraft. And in this graphic, you can see along one of the solar arrays here, the silver kind of triangular component coming off, that's the MAG boom that's located on the end of the solar array. Now, Juno utilizes the dual magnetometer technique by having an outboard mag right on the end of that boom, and then another inboard mag that's about halfway down that boom as well. The interesting thing about Juno is that although we're out on a boom and we're so far, we're still worried about having those accurate attitude determinations. And the solar arrays of Juno actually flex a little bit due to the pressure based on how large their surface area is. And so for that reason, there's actually star cameras on the end of the boom as well, so that we maintain that high accurate measurement as far as attitude is concerned. On the right here is a picture of the MAVEN spacecraft while it's in the clean room prior to launch. And MAVEN has 2 magnetometers, as I've shown you, but instead of being along the same boom, they're actually on either side of the spacecraft. So MAVEN essentially has these solar array arms that come off with these solar panels on either side, and it's a symmetric spacecraft. So you're only seeing one side of it here, but the other side looks exactly the same. We have the magnetometer right on the end here, and you can see the caution tape essentially on the sensor itself so that nobody walks into it. But these are boomlets that come off the end of the solar arrays. They're about 0.66 meter in length, and there's one on either side just to kind of give us a little boost away from the solar arrays and the spacecraft body itself. Now, the InSight magnetometer, developed by UCLA, is currently exploring the surface of Mars, and this is a lander, so it's not moving on the surface of Mars, it's just staying put in the same region, but the InSight magnetometer is body mounted as well, so is body mounted on the lander, so it's under the deck here. And so of course, as we're thinking about magnetic cleanliness, each of these missions kind of pose their own challenges that you have to think about when considering how to get those accurate measurements. So as far as pre-flight instrument calibration is concerned, I mentioned that we want to calibrate the instrument's orthogonality, the scale factor of the instruments, because it's not an absolute measurement that we're getting here. So we need to understand those scale factors, but we also want to understand what the offsets of our measurements are as well prior to launch. And in order to do this, we utilize large coil facilities that are able to eliminate the Earth's field and enable that measurement of the weak field with a high degree of accuracy. And so I'm showing you a picture on the right here of just one example of these large coil facilities, and it's one that we happen to use within my group at Goddard. It's the Mario Acuna facility at NASA Goddard. And so there are various buildings at this test site. with different size coils used for different purposes. But the one that I'm showing you here are 4 22-foot Brownback coils that are used to cancel the external magnetic fields in order to calibrate magnetometers. And so what we do is we apply a field about 50,000 nanotesla or stronger in order to optimize the signal to noise ratio of the measurements and calibrate the orthogonality, the scale factors, and the offsets of the instruments. But then in-flight calibration is also necessary for the offsets. So we're not calibrating the orthogonality or the scale factors in flight, but we are calibrating the offsets still. And they need to be calibrated essentially because they might vary in flight due to the ring core's response to the environment. And so that permalloy material that I talked to you about, the heart of the ring core, due to different environmental changes, it might affect how the magnetometer, the offsets of the measurements are being measured here. And so that has to do with maybe changes in temperature or radiation of the environment. And so it's something that we're able to calibrate in flight. And we do this by performing the calibrations in a rotating magnetic field that has a steady magnitude. And there are several ways to do this, and I'll talk to you about that in a second. But the calibration techniques are actually going to depend on the spacecraft dynamics and the capabilities. So is it a spinning spacecraft or is it a 3-axis stabilized spacecraft? Does the spacecraft have pointing requirements? These are all things that we need to think about. And so the different ways of performing this in-flight magnetometer offset calibration includes mag rolls, where we actually spin the spacecraft. I'll show you an example of that just after this on the next slide, but that's something that we perform regularly with MAVEN. We can utilize alphanic fluctuations in the solar wind to give us that rotating magnetic field without much of a change in the field magnitude. The Parker mission, although it does perform mag rolls, they also utilize the alphanic fluctuations for calibration as well. And then current sheet crossings, specifically within a magnetotail, is something that can be utilized as well. Juno is an example of this. Juno is a spinning spacecraft, and so the calibration to a certain extent can be performed just by the spacecraft spinning itself. But we're able to utilize the current sheet crossings in the Jovian magnetotail, which is essentially, for best case scenario, symmetric on either side of the current sheet. You get that rotating field that won't change much in magnitude. And that allows you to get another axis in that calibration there, because we want to calibrate all 3 axes. And so also, if it's available, straw electron measurements can provide a course independent check of the in-flight offset determination and how well we're determining those vectors. And so that's something that we're able to do on the MAVEN mission, because the straw electrons will follow the magnetic field pretty tightly. And so we can use our electron observations to have another assessment of the in-flight calibration. Okay, and so just one example of mag rolls, MAVEN actually regularly executes mag rolls to determine the change in the offsets. And so these mag rolls are performed by rotating the spacecraft about 2 different axes in a steady background field. And so that's something that you really need to consider is what environment are you sampling and how steady is the background field? So I'm showing you a graphic of the Mars magnetosphere here, just to kind of illustrate how different some of these areas are. And so MAVEN's orbit actually processes around the planet. So we're not always measuring the solar wind. We're not always measuring downtail in the magnetotail as well. And we need to consider this orbital precession to determine which environment we want to execute these rolls in. And so as you can see, here's MAVEN performing a spacecraft roll and coming in. The solar wind is the ideal environment at Mars to perform these mag rolls in order to calibrate our offsets of the instrument. And so we regularly execute these mag rolls in the solar wind when available. Every now and again, we're a little unlucky and we might execute the mag rolls in the foreshock where there is more turbulence, but for the most part, the solar wind has been the area where we've been most successful with identifying that steady field. Obviously, the magnetosheath is a turbulent area that wouldn't offer that rotating field with the steady magnitude there. And we have actually executed a few mag rolls in the magnetotail of Mars, and that might work pretty well in an intrinsic magnetosphere where the background field is pretty steady. However, at Mars, the environment is very dynamic because there are crustal magnetic fields that are rotating with the planet. And then much of the background field is also driven by the IMF and changes in direction there. And so in a few attempts of our mag rolls in the tail, we've been able to utilize that data, but it's just not as reliable as in the solar wind. And so we like to stick with the solar wind when that's possible with the mission. And here is an example of MAVEN mag roll results. So the results that you see here were spacecraft rolls that were performed during the cruise phase. So they were taken out in the solar wind during cruise. The time series that you see on the left is in spacecraft payload coordinates. And you can see right away these sinusoidal waves that you see are the spacecraft actually rolling in two different directions. So you see, I believe it's 12 consecutive rolls about one axis of the spacecraft, and then another 12 in the other axis of the spacecraft. And so we perform these rolls to determine what our offsets are. We apply an algorithm to determine what the offsets are, but we also look at these photograms as a diagnostic tool as well. And so I'm happy to report that over the course of the MAVEN mission, MAVEN has been at Mars for over 6 years at this point. MAVEN's mags have a combined offset variability of about 0.2 nanotesla in each axis. So they've barely changed, barely drifted over the course of a mission. And this is just a great result for Fluxgate magnetometers. So we were talking about the spacecraft generating fields that we can monitor as well. And I'd like to give you this example right here of observing reaction wheels. So reaction wheel assemblies can actually be observed by magnetometers when they're being operated within that frequency range that the mag is able to measure. And if you look at the data here on the left, what I'm showing you is a bow shock crossing of Mars that MAVEN observed. So starting at panel B, we have the BX, BY, BZ component in the Mars magnetospheric coordinate system, and then that total magnetic field. So you see this discontinuity right here where my cursor is showing you, that's the bow shock crossing itself. But if we zoom in, as we did right here, into that BY component, all of a sudden you see various waves at different frequencies that pop up as well. So when we analyze with this wavelet spectra, we can understand a little bit more what's going on here. Now, right around this red circle, we're seeing actual plasma waves. We're seeing 0.1 hertz waves down here at the bottom, and then we see 1 hertz waves, which are two different types of waves that are often present near the Martian bow shock. If you look over to this yellow circle, inside there, you'll see the low amplitude reaction wheel signatures that are observed at about 0.5 hertz, then again at 1.5 hertz, and then you'll see the tone rising up to about 5 hertz. And so this is actually something that we knew we'd be able to observe when they were operating within the frequency of the magnetometers. And it's something that we document as well. We don't necessarily remove it from the data, but the frequencies are archived at the PDS. So if anybody's ever analyzing mag data and you see something like this that you can tell is likely artificial, you can check the ancillary data to see if the reaction wheels were operating at that point in time. Another spacecraft field that we observe are the thruster fires as well. So I'm showing you another example here, but these are easily recognized signatures that we observe in the magnetic field data whenever MAVEN's thrusters are fired. And so they produce a signal that's about 6 nanotesla in amplitude, and that signal will last for the duration of the thruster fire burn. So looking at the time series, again, up on the top here, we have that BX, BY, BZ component in the magnetospheric coordinate system with the total magnetic field. And so if you're looking at all of the turbulence and all of the waves that are occurring here, suddenly you see this packet that pops up, and you might think that it is something that you'd want to study scientifically until you zoom in and you see on the bottom panel here that they really look artificial. And so that's an indicator that something was likely going on with the spacecraft. And once again, these are documented in the what we call the mission events so that we understand what spacecraft ops were going on at the time. And that's available on the MAVEN public SDC. And so I would like to just shift gears to talking about some of the magnetospheric discoveries that were made possible with magnetometers on board various missions throughout the solar system. And this is, of course, not a complete list. And These are all really exciting, but there's exciting discoveries that I didn't have time to get into today either. But just to give you some examples, pretty much almost at every planet, different discoveries that were made thanks to magnetometers being flown on missions. Starting with Mercury, messenger measurements below 200 kilometers revealed remnant magnetic fields that were locked in the crust of Mercury. You can see these measurements over here on the left, thanks to this publication by Catherine Johnson et al. And at the top here, she's plotting that radial magnetic field vector in black along, the radial magnetic field in black along with the model in the red curve. And in the next panel, a high pass filter was applied to the data in order to see those remnant fields really pop up. And these are important because the measurements help to constrain an understanding of the history of Mercury's magnetic field. And in this paper, they suggest that a dynamo was likely present at Mercury 3.7 to 3.9 billion years ago, and that dynamo could have generated a magnetic field that was as strong as Earth's dipole field today. As far as flux ropes are concerned, Pioneer Venus Orbiter revealed magnetic flux ropes in the dayside ionosphere of Venus. Showing you the first examples of flux ropes here, the total field strength is shown going from roughly 0 nanotesla all the way up to 50, 60 nanotesla throughout the duration of this crossing through the dayside ionosphere of Venus. Looking at the right, you can see from these photograms of the magnetic field measurements just a nice rotation of the magnetic flux ropes, demonstrating that they are helical cylindrical structures deep within the ionosphere. And so it was determined that the presence and the altitude of these flux ropes actually vary with solar wind pressure, and that the magnetized state of Venus dramatically changes. And so this was a really important discovery to be made at Venus. So you can see through the bottom panel here, the 3 different figures have varying solar wind pressure as you go from left to right. And you'll understand that the background field isn't very strong to begin with, but you see all of these enhancements, these localized enhancements. Those are the flux ropes that are peaking out to, like I said, very strong background fields. But then as you move over to the right, you'll start to see less of the flux ropes, but Venus is becoming more magnetized. So its background strength is stronger and stronger until you get to the right, where you essentially don't see any flux ropes, but it has over 100 nanotesla in background field in the ionosphere. The crustal magnetic fields at Mars were discovered thanks to the Mars Global Surveyor, and they were mapped thanks to MGS as well. And they found that the regions of strong crustal magnetism actually correlated with ancient terrain. Showing you the orbits of MGS on the left here, these projections of the orbit of MGS with the vector magnetic fields added to the orbit as well. You can see through periapsis as the spacecraft came close to the planet, all of a sudden the vectors started changing dramatically with these rotations, and that was thanks to the crustal magnetic fields at Mars that were discovered. On the right, here are statistics of the magnetic field and how it's mapped over the surface. So red and blue show the strength and the direction of the radial magnetic field going into and out of the page. And you'll see that it's correlated with the different features on the Martian surface. And this is how they identified that the strong magnetic field regions actually correlated with the ancient regions on the surface of Mars. Now, showing you on the left here, continuing with the crustal fields at Mars just for a second, this is the finalized crustal magnetic field map thanks to the mapping performed by the MGS mission, again showing the radial field, but it just demonstrates to you how non-uniform this magnetic environment is at Mars compared to many of the other planets that have intrinsic magnetic fields. And so these strong crustal fields rotate with the planet and create an obstacle to the solar wind that's always changing. Now with MAVEN, we're still observing the crustal magnetic fields at Mars, and at our periapsis altitudes of about 150 kilometers, we can measure the strongest crustal fields to be around 1,000 nanotesla in strength. And I really like this graphic that you see on the left here, showing you just the way that the crustal magnetic fields rotate as we measure them. So this is through one of MAVEN's periapsis passes, but then the arrows that you see kind of swirling out from there, growing in strength because the magnitude is growing, are those strong crustal magnetic fields. With the Juno mission, we're able to constrain Jupiter's magnetic field, and Juno measurements have revealed details about the complexity of the magnetic field at Jupiter. So the results have enabled higher order modeling of the field, but they also provide details about the internal structure of Jupiter itself and its dynamo. Looking at the figure on the right here, you'll see what the modeling of Jupiter's magnetic field looked like prior to Juno. And then as we add more and more orbits, you can see that some of the complex structure of the magnetic field itself has started to come out. And even more so is as Juno continues to orbit Jupiter and increase statistics, that will allow for future investigation of the secular variation of the Jovian magnetic field. Now, as far as Ganymede's intrinsic magnetic field is concerned, this was discovered by Kivelson et al. After 2 flybys of Galileo past Ganymede. And so the interesting thing here is that the equatorial surface strength of Ganymede is about 750 nanotesla, which is much stronger than the intrinsic magnetic field of Mercury itself. And they also found that this magnetic field was tilted by about 10 degrees from the rotation axis of Ganymede. Looking at the left, again, here are the orbits of Ganymede, the flybys, excuse me, of Galileo past Ganymede, so that we can see that intrinsic magnetic field being observed. And you'll just notice how the direction of the vectors change as you get closer to the moon and also grow in strength to measure that magnetic field. On the right is the time series of the data plotted along with the model so that you can see that nice dipolar field that was observed as well. For Saturn, Cassini's grand finale orbits provided a unique opportunity to understand the magnetic field at Saturn. And these measurements took place between Saturn and its rings. And this enabled the authors, Michel Daugherty et al., to study both the internal structure and the local magnetic field environment. So if you look at the figures here, there's a lot to learn because these were some of the closest magnetic field measurements taken at Saturn. And so they were able to study the interior of the planet itself. They were able to look at auroral field aligned currents and understand how they're generated. But another interesting point is that these measurements confirmed that the magnetic axis of Saturn is aligned with the rotation axis. And this is important because it actually challenges and opposes some current dynamo theories. So we really aren't necessarily sure how some of these dynamos actually work at various planets. Now, the ice giants offer very unusual geometries as far as magnetic fields and planetary magnetospheres are concerned, because both Uranus and Neptune have offset tilted dipole fields. And not only are their fields offset and tilted, but their planetary rotation axes are highly inclined as well. And you can get a sense of the geometry and what's going on by looking at these 2 figures on the left here, one for Uranus and one for Neptune as well. And the time series that I'm showing you for each are the single flybys of the Voyager 2 spacecraft by Uranus and by Neptune. Now, these time series are the only in situ magnetic field measurements that exist at these 2 planets, because Voyager was the only spacecraft to measure and to visit them. And so these are the only magnetic field measurements that exist so far, and you're looking at them. However, it's possible to still find some new evidence of magnetospheric processes by revisiting this data. And I'm just showing you a cartoon over here on the right of the Uranus magnetosphere, but a recent publication by Dan Gershman and myself led to a new observation of a plasmoid within the magnetotail of Uranus as well. And so finally, thanks to the Voyager 1 magnetometer, we were able to observe crossing of the termination shock as Voyager left the heliosphere at a distance of 94 AU. So the crossing occurred as the spacecraft moved from the solar wind at the extent of our heliosphere and crossed into the heliosheath. And I'm showing you the data here. On the left are the mag data with the angles plotted and the total field magnitude at the top. But you should see that the total field magnitude is a 24-hour average, and that's because we're really measuring at the level of 0.1 nanotesla here. And so we need those statistics in order to understand what's going on. Over on the right, they're utilizing the total field magnitude again, but looking at the cosmic ray intensity too to confirm that the termination shock was crossed. And so just to summarize here, as far as Fluxgate magnetometers are concerned, measuring magnetic fields provide crucial information about the environment both within and around objects in our solar system. And Fluxgate magnetometers measure this magnetic field strength and direction. The ring core fluxgates are what I really went into detail here because they're the most common type that are used for space exploration. Fluxgates offer a low mass and a low power option. And what I didn't get into, but I'll say really quickly, is that a low cost option as well. Small fluxgates are available for resource constrained missions. And then magnetic control plans and calibration are crucial for those high accuracy measurements. And as I showed in the last few slides, countless discoveries have been made with these space-based magnetometers, and they're continuing to be made as well. And with that, I would like to stop and say thank you and take any questions.
All right, thanks, Gina. That was a great talk. Found it really informative, and it's always nice to get a perspective outside of Earth's magnetosphere here. So thank you very much. So we do have a handful of questions that I'll go through. I believe there are some other team members that have attended from your group. So if they also want to unmute and answer any questions as well, I welcome that. So our first question comes from David Miles. And this is around slide 14. Did you move the nested double wound sensor design to minimize the number of cores used for an instrumental reason? For example, compactness or 2 axes of feedback?
That is a great question and very technical. And if you don't mind, I will kick that to Dave Shepard, our engineer, if he happens to be on the line.
I actually don't see Dave Shepard.
Okay. I honestly am probably not the best person to answer that question for you. So if you don't mind, I would love to talk to Dave and get back to you about that.
Okay, that's perfect. I will also direct David to David Shepard as well.
Yes, perfect.
So Eric Lund had a question, but you answered it a few slides later.
Great.
Mark Moldwin had another question. What amplitude of the temperature control can you get with the non-magnetic resistive heating tape? So another fairly technical question.
Again, yes. I mean, these are all wonderful. Unfortunately, I wish that my engineers were on here because, as I mentioned in the beginning, since I am part of a bigger team, I am not actually the one in the lab building the hardware itself. So again, if we can make note of this question, I would love to get back to you, Mark.
So Lynn Wilson has a question. I think it's a little, it has to do with the redundancy of the magnetometers. Okay. Why not use 3 combos of the magnetometers that you have with the 2 sense units to get redundancy in each component? Does this just create extra noise or artifacts, or is it just a mass cost issue?
Yeah, I mean, essentially, the reason why we use the 2 sense units around the single ring core is because then rather than having to fly 3 of those sets, we're able to fly 2 and get those 3 axes. And so it allows us to have that lower mass. And so there's really not a need to have the redundancy in the different axes. In fact, we just use 3 axes. And when we have those sense units around the ring core, we're utilizing those inner sense units for the measurements because those will be slightly more accurate than the outer sense units. So we have 2 of the inner sense units that we use, and then 1 of the outer sense units for that 3rd component as well.
Thank you. So Laura Oeda, I hope I pronounced that right, had a question about the noise floor of the 0.5-inch magnetometer and roughly what that noise floor is. I believe you may have addressed this on slide 17.
Yeah, so we were talking about the capability of the measurement being about 0.1 nanotesla. I do, if I can just advance though, it sounds like people might be interested. We do have a few more stats that I can share here about the small Fluxgate specs that our engineers have gathered based on testing in the lab. So I can leave that up, hopefully, to answer some of the questions that might pop up on those.
Okay, excellent, thanks. JA had a question regarding the dual magnetometer method and whether or not it's effective or ineffective for cubes.
That's a good question. I think. Oh, sorry, go ahead.
No, sorry, I interrupted you.
Sure, no worries. Yeah, I think it depends. It all comes back to the mission measurement requirements. And so typically for a lot of the CubeSat missions, you won't have as stringent of measurement requirements as you would for some of the, flagship missions, for instance. And you might want to utilize that, but it also, that dual magnetometer method is based off of the assumption that the spacecraft field goes off as a dipole. And so I'm assuming that that assumption has been used from observations of standard size spacecraft, not so much CubeSats. I would say you could probably use that same estimation, but it might not be necessary for the actual measurement requirements that you're trying to meet for the small sat missions.
Thank you. So John Hedusik is also asking about the dual magnetometers. On MAVEN, how does the second magnetometer help correct for the interference if the magnetometers are both the same distance from the spacecraft center?
Yeah, and so essentially it helps us to understand the field given off by the body of the spacecraft, not using the dual magnetometer technique per se, but it gives us essentially two data points of both the ambient field and the spacecraft body as well. Plus, if different things have occurred on the solar arrays, for instance, if there's a change, the magnetic source of the solar arrays can be measured more closely by one of the magnetometers versus the other. And so at this point, so far into the MAVEN mission, we're really just utilizing one of the magnetometers. It was essentially for a redundancy sanity check of what's going on there. And since we understand the environment and the spacecraft at this point, we're really just using one of the magnetometers.
Excellent. So Dave Miles has another question regarding offset. On an order of magnitude, how much do you typically see, and do you guys have a sense for the origin of where this offset is coming? I believe this may have come up, or you may have answered part of this around slide 27 or 28.
Yeah, so at least as far as MAVEN is concerned, because we get these consistent mag roll opportunities and they're executed, we can say with great confidence that the offset has, as I showed, about 0.2 nanotesla in each axis over the mission lifetime of 6+ years. And so, sorry, I'm forgetting the rest of the question there.
Do you have a sense of where it might be coming from, the offset?
Yeah, so as far as the offset is concerned, where it could come from, I mean, we have a little bit of activity on the solar arrays that we're monitoring, and so that has changed over the mission lifetime, which could induce a field that we're measuring with our magnetometers as well. But I think it also just could really be from that permalloy material in the ring core responding to the environment that we're flying it in. And so luckily, Mars itself isn't a high temperature environment or a high radiation environment, but there are still some temperature changes and whatnot that can affect the material.
Yep. So following on calibration again, Ankush is asking, how frequently are calibrations typically performed?
Yeah, so as far as the in-flight calibrations are concerned, I'll speak to MAVEN just because we have a really nice calibration schedule going with that mission. But we started pretty frequently in the beginning of the mission. I would say it was, I believe once every 3 or 4 months, so several times a year. We do use fuel though to roll the spacecraft, and so that's another mission requirement that needs to be considered. And so at this point, we're trying to conserve the fuel for the mission, and we're down to about 1 mag roll every 6 months. And that changes based on where the orbit is. If we're in the solar wind where we want to perform the mag rolls, then we do. But if we're not in an ideal environment, then we will just wait until we can get there. So at this point, we're at a cadence of about every 6 months.
Excellent. So I'm going to jump to another question that kind of follows on to this before going on to the others. John Hadusik asks, what is the benefit of doing the mag rolls in the Martian magnetotail if the quality of the calibration is lower than elsewhere in the Mars?
Sure. Yeah. So we essentially attempted to do them in the magnetotail because the orbit configuration of MAVEN was such that we wouldn't be in the solar wind for an extended period of time, just because periapsis was on the day side, so we were deep within the tail. And we wanted to try to get a mag roll in just to see what our offsets looked like. And so I believe we only tried this perhaps twice. And one time it was pretty good, the other time not so much. And then we just decided that because it is more of a dynamic environment, that we would not utilize the spacecraft resources anymore for that, and that we would just wait until we're out in the solar wind. But just because of the orbital precession of MAVEN, we can go without being in the solar wind for a month or 2 at a time.
Excellent. So Eric Lund has a follow-up question. What limits the frequency response of a typical Fluxgate magnetometer?
Oh, this is another question where I need my engineer on here. Yeah, I'm going to punt that one too, if that's okay.
Okay, yeah, absolutely. So Ankush is asking about the Mercury dynamo and with reference to slide 31, and how are we able to estimate the age of that dynamo with magnetometers?
Sure. I'm going to point you to that paper as well. Unfortunately, I wasn't actually on that study. I do know the authors, but I'll point you to them since they are the experts there.
Thank you. So Patricia is asking a pretty loaded question. Can you give the basic difference between a Fluxgate and search coil magnetometer? I will say to everyone that next week, George Hadosky will be talking about search coils. So maybe we'll leave that question until next week, as it is a fairly loaded one, if that's okay with you, Gina.
That would be great, because I actually plan to dial in and learn about them as well.
Okay. My internet cut out there, but I heard that would be great. So
yeah.
So our last question comes from Marius. Are Fluxgate magnetometers affected by internal or surface charging on the spacecraft?
Yeah, so any kind of charging that occurs that could generate currents and magnetic fields, for most spacecraft, at least that I've been involved in, the charging has been mitigated for the most part, and the environments that I investigate, we don't have to worry about. But yeah, I mean, that's something that we always want to consider, not just for measurements, but for the safety of the instruments as well.
Excellent. All right, thank you. So I think that sums today. Thank you for a wonderful talk, and thank you for staying to answer the questions past the
Absolutely.
hour. As I mentioned, next week, George Hospodarsky, I hope I pronounced that last name correct, he'll be discussing search coil magnetometers. So if you're interested in continuing with the instrument talks that we've been doing, please attend next week. And thank you again, Gina.
Thank you so much.